the last class we are looking at this one dimensional general one dimensional boundary value problem, and also we looked at some applications like steady state heat flow problem. And let me summarize what we have done in the last class. This is a equation representing general one dimensional boundary value problem, and the domain is also indicated there. X is going from x0 to xl, and these are the boundary conditions at x is equal to x0, where t is the field variable here. If it is a steady state heat flow problem, then T is temperature. In the last class we have looked at steady state heat conduction problem, and here either the boundary conditions can be essential boundary conditions or natural boundary conditions. These are the boundary condition at x is equal to x0, where k naught is k value evaluated at x is equal to x0, and the boundary condition at the other end at x is equal to xl is given by this one, where kl is k evaluated at x is equal to l. Either it can be, the boundary conditions can be either essential boundary conditions or natural boundary conditions. So what we did is we applied Rayleigh-Ridge method, and we found equivalent functional before we proceeded and substituted finite element approximations in terms of linear element, two node linear element, finite element approximation of t and derivative of t. So equivalent functional that we obtained in the last class using Rayleigh-Ridge method is given here, and then what we did is we substituted finite element approximations of t and also derivative of t, and we have taken a two node linear element, and when we made substitution of finite element approximations, we get I equivalent functional in terms of the nodal values. So after that what we did is we applied stationarity condition, that is partial derivative of I with respect to d should be equal to 0, where d is a vector consisting of nodal values, and we obtained this equation where the contributions to the stiffness like matrix is coming from various components k, kp, k alpha, and force like vector contribution is coming from rq and r beta, which are given or which are shown on the slide there. So this is the element equations for a two node element for general one dimensional boundary value problem that we derived in the last class, and we obtained this element equations using Rayleigh-Ridge method, but we can also apply Galerkin method to get similar kind of equations. So now later what we did in the last class is we applied the whatever we developed element equations for general one dimensional boundary value problem using two node linear element, we applied to steady state heat conduction problem. The governing equation for steady state heat conduction problem is given by this differential equation, where k is kxx is thermal conductivity, T is the temperature, Q is the heat generated per unit volume, and these are the boundary conditions, either T can be specified or heat flow can be specified, that is either essential boundary condition or natural boundary conditions can be specified. So these are the boundary conditions and the differential equation is shown there. So what we did in the last class is we made a comparison between the corresponding quantities in the general one dimensional boundary value problem and the corresponding variables in the steady state heat conduction problem, and we came up with this comparative table. So what we can do is, once we have this comparative table, we can take the element equations that we have for one dimensional boundary value problem and make substitution with the corresponding variable for a specific problem. Here it is heat conduction problem. So once we do that, we get the element equations for heat conduction problem. So we do not need to repeat the entire procedure each time. So this is the element equations that we have for general one dimensional boundary value problem. Now we need to make substitution of the corresponding variables corresponding to the heat conduction problem, steady state heat conduction problem that we are looking at, and when we do that substitution we get this element equations. So this is what we obtained in the last class, and using this we also solved one example to see the application of this whatever element equations that we developed. So now we will, in this class we are going to continue further, look at some more applications. So in today's class we will look at one dimensional heat conduction convection problem. The governing equation for heat conduction and convection can be derived simply by accounting for the heat loss due to convection in the energy equation. Considering one dimensional solution domain as shown in figure, heat loss due to convection QH is equal to H times T minus T infinity, where T infinity is temperature of surrounding fluid, H is the convection coefficient. So using this, from conservation of energy we can write this differential equation for this case, heat conduction and convection case, where the coefficients k xx t or the parameters k xx t q all have same meaning as what we have seen already for steady state heat conduction problem. In this equation, P is parameter over which convection takes place, and other quantities have similar kind of meaning as what we have used for steady state heat conduction problem. Kxx is temperature thermal conductivity in x direction, because this is 1D problem, and T is temperature, and Q is heat generated per unit volume. So now in this differential equation, if we set derivative of T with respect to time equal to 0, we get in this equation by setting dt d capital T over d small t equal to 0, steady state equation can be obtained, which is shown there. So now let us look at what are the boundary conditions. Boundary conditions can be one of the following: either temperature specified or heat flow specified. First one is essential boundary condition, second one is natural boundary condition. So, now for this particular case of heat conduction and convection, we can obtain element equations by making a comparative table between the corresponding quantities in the general one dimensional boundary value problem and the variables in this particular case. So, this boundary value problem is similar to general boundary value problem if variable are interpreted as shown in the table here. So, once we identify the corresponding quantities, we can make substitution or plug in into the element equations that we have for general one dimensional boundary value problem. This is the element equation that we have for general one dimensional boundary value problem. Now, we need to make substitution of the corresponding variables for this particular heat conduction convection problem. When we make that substitution, the following finite element equations can be written directly from general equations after making substitution. So, this is the element equation for heat conduction convection problem if we adopt 2 node finite element for discretization. So, now let us look at the application of this equation by looking at an problem. Now, let us take an example. Determine steady state temperature distribution in a thin rectangular film shown in figure below, which is shown there. The fin is 120 mm long and 160 mm wide and 1.25 mm thick. The inside wall is at a temperature of 330 degrees centigrade. The ambient air temperature is 30 degrees centigrade, and other quantities like thermal conductivity, convection coefficient are given. So, now we need to discretize this problem before we apply the element equations that we derived for 2 node finite element. So, this is the figure which is showing the rectangular fin with all detail. And now, before we discretize, the problem can be treated as one dimensional problem if convection at the ends is neglected. So, this is one of the assumptions. So, once we treat it as one dimensional problem, a one dimensional finite element model using 3 linear elements is shown. Here T1 is shown as 300 degrees centigrade, it is a mistake, it should be 330 degrees centigrade, and at the other end essential boundary condition is specified, T infinity is equal to 30 degrees centigrade. So, at T1 we have 330 degrees centigrade, at T4 we have 30 degrees centigrade, and total length of rectangular fin is 120 millimeters, and it is discretized using 3 elements, and each element has 2 nodes, and length of each element is 120 divided by 340 millimeters. Since the material properties like thermal conductivity, convection coefficient, and also since the length of each element is same, element equations are going to be identical for all the 3 elements. So, now let us look at each of the element. Length of each element 40 millimeters, area of cross section 160 multiplied by 1.25 millimeter square. Since convection at the ends is neglected, convection at the top and bottom of fin, convection from top and bottom of the fin is going to depend on perimeter P, and here perimeter value per unit length is given or calculated, and here there is no heat generation. So, Q capital Q is equal to 0. So, making substitution of all these things into the element equations for heat conduction convection problem that we already have, we get element equations for this particular problem. And as I mentioned, all elements are identical. So, element equations are as follows, where K is stiffness like matrix, making substitution of all the quantities and simplifying it further, we get this K, and R again making substitution of all quantities like convection coefficient, perimeter, ambient temperature, area of cross section, length of each element, we get this R. Now, this K and R are going to be same for all elements because all elements are identical. So, now assembling global equations, we get this. There are 3 elements and each element has 2 nodes. Element 1 contribution goes into 1 and 2 rows and columns, element 2 contribution goes into 2 and 3 rows and columns, element 3 contribution goes into 3 and 4 rows and columns. So, with that understanding, after assembling the global equations looks like this, and now making or imposing the essential boundary condition, that is T1 is equal to 330 degrees centigrade and T4 is equal to 30 degrees centigrade, which are given. Essential boundary conditions require that T1 is equal to 30 degrees centigrade and T4 is equal to T1 is equal to 330 degrees centigrade and T4 is equal to 30 degrees centigrade. So, substituting these values, and since the temperature value is specified at T1 at node 1 and node 4, that is T1 and T4 are known, we can eliminate first and fourth equations and we can get this reduced equation system, which we can manipulate by moving the known quantities to the left hand side, and we obtain this equation, and solving this equation we can obtain what is T2 and T3. So, solution of T2, temperature at node 2 and temperature at node 3 are given in the slide there. So, now we solve this problem and we just calculated T2 and T3 and T1, T4 are imposed. So, complete solution we can plot. Complete solution is plotted in figure below, that is T1, T2, T3 and T4 values, temperature on y axis and distance on x axis. So, now this is one application of general one dimensional boundary value problem that we are looking at, and here if you see this problem, at node 4 temperature is specified. Instead of that, we can also have convection boundary condition prescribed. So, now that is in the previous problem at T4 we have essential boundary condition specified. So, now what we will do is we will look at the case when natural boundary condition is specified at node 4. So, heat flow through thin fins with convection boundary condition at free end. So, in the previous example, a specified temperature equal to ambient temperature was used as boundary condition at the free end. A convection boundary condition is perhaps more appropriate for this end. So, in this we are going to assume, or this boundary condition can be represented as, this is the convection boundary condition. So, instead of T4 being specified as essential boundary condition, if T4 is specified as natural boundary condition, then the element equations are going to change a little bit. Since node 4 corresponds to element 3 and element 1 and 2 equations remain same as what we have seen in the last example, and element 3 which consists of node 4, we need to have this boundary condition. So, element equations for that particular element 3 are going to be different little bit, because we need to include these boundary conditions. Comparing with the general form of a natural boundary condition, we have already the element equations for general one dimensional boundary value problem. So, now with this natural boundary condition, that is convection boundary condition at node 4 or at one of the ends, what we can do is we can make a comparison with the general one dimensional boundary value problem and identify the corresponding coefficient corresponding variables, and then we can develop the element equations for this particular problem. So, the equation that we obtained for general one dimensional boundary value problem with k, p, q, alphas and betas are shown. So, now making a comparison, alpha L is nothing but it is going to be alpha 1, beta L is nothing but beta 1, sorry, alpha L is nothing but alpha 2 and beta L is nothing but beta 2. So, making, and alpha 1 and beta 1 are going to be 0. So, making these substitutions into the general one dimensional boundary value problem element equations, we notice that now element equations consists of k alpha and r beta terms, because in the previous example where we do not have this convection boundary condition, alpha 1 alpha 2 both are 0 and beta 1 beta 2 both are 0. So, those two that matrix consisting of alphas and vector consisting of betas, contribution of those we have not seen, but for this particular problem where alpha L which is alpha 2 and beta L which is beta 2 are given. So, these are non-zero, So, element equations now contain k alpha and r beta terms. So, now with that understanding we will go back to the previous example and solve it, except that now we have the convection boundary condition, which is natural boundary condition specified at one of the ends. So, now let us take the same discretization. 3 element finite element model for the fin is shown in figure, and T1 is equal to, T1 is given already 330 degrees centigrade, and T4 now we need to apply this convection boundary condition, which is natural boundary condition, and element 1, element 2, the element equations are going to be identical to what we already have for the previous example, and element 3 element equations are going to get modified little bit because of contribution from k alpha and r beta. So, element equations for element 1 and 2 just they are repeated here, which are obtained in the previous example. Element 3 same as elements 1 and 2, except also includes natural boundary condition term for node 2 of element k alpha and r beta. So, making this small change we get the element equations corresponding to element 3. So, now with the same reasoning as what we have for the previous example, element 1 contribution goes into 1 and 2 rows and columns, element 2 contribution goes into 2 and 3 rows and columns, element 3 contribution goes into 3 and 4 rows and columns, and putting at the appropriate location the corresponding contribution, we get this global equations. And now only one essential boundary condition is given, which is T1 is equal to 330 degrees centigrade. Essential boundary condition requires that T1 is equal to 330 degrees centigrade. So, removing the first equation we get, and rearranging it and solving, rearranging and solving, we can obtain what is T2, T3 and T4. So, solution of T2, T3, T4 is given, and if you see or if you compare this solution with what we already have for the case when at T4 at node 4 we have essential boundary condition specified ambient temperature in the previous example. If you compare solution of both these cases, the solution is comparable to one obtained using ambient temperature boundary condition at the outer end of the fin. Both are almost equal, thus this choice of boundary condition was not crucial for this particular problem. So, maybe in this particular case the choice of boundary condition, that is whether you apply convection boundary condition or ambient temperature boundary condition, almost same equation can be obtained. So, now let us look at another example or another application of what we have already seen, that is general one dimensional boundary value problem application to structural mechanics problem. So, in this case what we will be doing is we will be considering a column buckling problem. Consider calculation of buckling load for a simply supported column shown in figure below. So, a member which is subjected to axial compressive load like this can be classified as a column. So, length of column is L, EI is constant and x axis is shown along centroidal axis of the member, and W is shown perpendicular to x axis, and P is the load that is applied at one end. So, this is simply supported column, and if you observe the boundary conditions, W at both ends is equal to 0 and also curvature at both ends is going to be 0. So, now if you look at the Gaussian differential equation for this particular problem, it is going to be fourth order equation. So, what we will be doing is we have the element equations corresponding to one dimensional general one dimensional boundary value problem. We will see if the differential equation for this particular problem we can put into the form similar to general one dimensional boundary value problem and identify the corresponding variables, and then we can develop the element equations for this particular column buckling problem. And once we decide the discretization, how many number of elements we want to use, we can get the element equation for each of the elements, and then we can assemble the global equations, apply the boundary conditions, we can solve for the problem. So, now let us look at the Gaussian differential equation for this problem, which is a fourth order differential equation where E is the Young's modulus, I is moment of inertia of cross section, W is transverse displacement, and if the column has constant AI, then we can take EI out of the differentiation operator and this equation becomes this one. And now we got the differential equation. This differential equation has to be satisfied from x going from 0 to L. The boundary conditions, if you look at the problem or the schematic, once again we can write the boundary conditions. W at x is equal to 0, W at x is equal to L is equal to 0, and second derivative of W at x is equal to 0, second derivative of W at x is equal to L also should be equal to 0. The first boundary condition is essential boundary condition, second boundary condition is natural boundary condition. You can easily recall the thumb rule that we discussed in the first classes. If a differential equation is of order 2p, those boundary conditions of order 0 to p minus 1 are essential, and those boundary conditions from p to 2p minus 1 are natural boundary conditions. So, here differential equation is of order 4, so 2p is equal to 4, so p is equal to 2. So, those boundary conditions of order 0 to p minus 1, which is 1, are essential. Those boundary conditions of order p, which is 2 to 2p minus 1, which is 3, are natural boundary conditions. So, you can also verify that thumb rule once again for this particular problem. So, now we got the boundary conditions and we have the differential equation for this problem, but only thing is this is a fourth order differential equation, whereas the general one dimensional boundary value problem that we looked at is a second order differential equation. So, somehow we need to make some substitution here to bring this fourth order to second order The problem can be converted into second order form if we define y is equal to second derivative of w with respect to x square. So then the given differential equation or the differential equation for this particular problem becomes, after making the substitution, becomes this one, and this is, we can make a comparison of this with the general one dimensional boundary value problem because both are second order differential equations. But now when we make this substitution, boundary conditions also changes. So the corresponding boundary conditions in terms of y are given here. We already know that second derivative of w with respect to x square at x is equal to 0, at x is equal to L are 0. So making this substitution, we get y at x is equal to 0, y at x is equal to L is equal to 0. And now the given differential equation, we can rearrange it by dividing the given differential equation or the differential equation with EI. We can write the problem statement in this manner: second derivative of y with respect to x square plus p over EI times y is equal to 0, that is the equation, differential equation that needs to be satisfied between x is equal to 0 and L, including x is equal to 0 and x is equal to L, and the boundary conditions are y evaluated at x is equal to 0, y evaluated at x is equal to L is equal to 0. So now what we need to do is, we need to make a comparison between this and general one dimensional boundary value problem. Comparing this equation with general form, we see that we can identify the corresponding variables, variable in general form and the corresponding variable in the buckling equation. So once we have this comparison, we can make substitution of the corresponding variable values or corresponding variable quantities into the element equations that we have for general one dimensional boundary value problem. So making, this is the general one dimensional boundary value problem element equation. Now making substitution of k, p, q into this equation, which are corresponding to the buckling problem, we get the finite element equations for a 2 node element of length L for buckling problem can be written like this. And here we do not know what p is, we need to determine p. Since p is not known, this is an eigenvalue problem. So this equation gives us an idea about element equations for a 2 node finite element for buckling problem. So now the given simply supported column of length L, we can discretize using some number of finite elements, and then we can use these element equations and get the global equations and solve for the problem. So now let us take an example on column buckling. A 4 element model for the problem is shown in figure. So simply supported column of length L is discretized using 4 elements, 4 linear elements or 5 nodes in total for this problem, and each of the elements are of same length, and length of each element is L over 4, and since length of each element is same and EI is constant, the element equations for all the elements are going to be identical, and we already have the element equations for column buckling problem for 2 node element, linear element. So now we can make substitution of the values into that equation, the element equations for one element by making substitution into the element equations that we obtained for column buckling problem from general one dimensional boundary value problem. We get these element equations for one element and all elements are identical, and we can rearrange this element equation in this manner for convenience. So, this is for one element, and after assembling global equations, after assembly the global equations looks like this. For this particular problem we have taken 4 element model. Element 1 contribution goes into 1 and 2 rows and columns, element 2 contribution goes into 2 and 3, element 3 contribution goes into 3 and 4, element 4 contribution goes into 4 and 5 rows and columns. With that understanding, if we assemble, after assembly the global equations looks like this. And now applying the boundary conditions require that y1 is equal to 0 and y5 is equal to 0. Boundary condition require that y1 is equal to 0, y5 is equal to 0. Therefore, eliminating first and fifth rows, the reduced equations can be obtained from the global equations, and here a substitution is made. Z is equal to PL square over 96 EI, and you can see here this is an eigenvalue problem. So, the eigenvalues can be computed by setting determinant of the matrix is equal to 0, determinant of matrix consisting of Z is equal to 0 because to have a non-trivial solution, determinant of matrix should be equal to 0, because trivial solution is y2, y3, y4 is equal to 0. That is not what we are looking for, we are looking for non-trivial solution. So, determinant of matrix should be equated to 0. Since this is a 3 by 3 matrix, we are going to get 3 roots or 3 eigenvalues. Eigenvalues are computed by setting determinant of matrix equal to 0. Therefore, we get this. When we do that, we are going to get a cubic equation. So, there we are going to get 3 roots for this cubic equation, and the lowest root corresponds to the first buckling mode of the column. So, the lowest root corresponds to the first buckling mode of the column. So, now Z is equal to PL square over 96 EI. So, what we will be doing is to calculate buckling load of the column, we equate the lowest eigenvalue to PL square over 96 EI, back calculate what is P, that is going to be the load at which column is going to buckle first. Lowest root corresponds to the first buckling mode of the column, thus buckling load for the column is given by equating the lowest eigenvalue to PL square over 96 EI and back calculating what is P, which is going to be the critical load at which column is going to buckle first. And if you compare this with the exact solution for this particular problem, which is same as for Euler buckling load for pin conditions of a column. So, the exact solution for this problem is given by P critical is equal to pi square ei over L square, and if we calculate what is this pi square, it is going to be 9.87 ei over L square. So, this is a critical theoretical value, critical load or theoretical value of critical load for this particular column with the end conditions as pin is given by this one. And whereas when we apply finite element method with 4 elements, 4 linear elements, we obtained P critical as 10.37 ei over L square, and if you find error in finite element solution that we obtained is about 5%. Error in finite element solution is about 5%. The buckling mode can be obtained, can be determined by finding the corresponding eigenvectors. So, we got the eigenvalues by making substitution of each eigenvalue back into the equation. We can determine what are the eigenvectors, corresponding eigenvectors. Substituting z is equal to 0.108 in the global equations we get, and again when we are solving for eigenvectors, one of the y values must be specified arbitrarily. So, we choose y2 is equal to 1 and solve for y3 and y4 from the second and third rows, and when we do that we get this equation by setting y2 is equal to 0 and eliminating or removing first equation. We can use the other two equations to solve for y3 and y4. Solution of this system of equations is y3 is equal to this and y4 is equal to this one. So, the lowest buckling mode by putting all the values y1, y2, y3, y4 and y5 values in a vector, we get the first or the lowest buckling mode vector like this, and similar calculations can be repeated for other eigenvalues, but since we are interested in critical load, we are looking at only the lowest eigenvalue and corresponding buckling mode. So, now if we repeat this problem using 2 elements, 3 elements and 4 elements, and this is how convergence looks like. To see the convergence of the solution, the problem is solved with 2, 3 and 4 elements. The following summary of results clearly shows that solution is converging fairly rapidly, and if you instead of 4 elements, if 2 elements are taken, P critical is P 12 ei over L square, that is what we obtain using 2 linear finite elements for this problem, and if you add up 3 linear elements, we get P critical as 10.8 ei over L square, 4 elements as the solution, finite element solution gives us P critical as 10.37 ei over L square, whereas the theoretical value is P critical is equal to pi square ei over L square, which is going to be 9.87 ei over L square. So, you can see the solution is converging fairly well, and here if you want more closer to 9.87 EI over L square, we can try this problem using 5 linear elements, or we can adopt higher order elements. Instead of linear element we can adopt quadratic elements, that is instead of 2 node elements we can go for 3 node elements. So in the next class we will be looking at higher order elements.